Use mathematical induction to prove this statement here. The sum of r from 1 to n of r 2r plus 6 is equal to 2/3 n, n plus 1, n plus 5. Now, proof by induction always follows the same 4 steps, no matter what we're trying to prove. So we start with the base case, step 1, and in this case, the smallest value that n can take is 1. Because r is starting at 1 and going up to n, the smallest n can be is 1. So that's what we're going to start with. On the left-hand side in that scenario, we have the sum from r equals 1 up to 1 of r, 2r plus 6. That means substitute 1 into this expression, so it's 1 plus 2 times 1 plus 6, and then add on the next one, which would be 2, but we have to stop at 1, so it's just that one. So it's 1 times 2 plus 6, which is 8, which is equal to 8. So when n is equal to 1, the left-hand side is equal to 8. The right-hand side is equal to 2/3 times 1 times 1 plus 1 times 1 plus 5. That's 2/3 times 1 times 2 times 6, which is 2/3 of 12, and 2/3 of 12 is indeed 8. So we have shown that the left-hand side is equal to 8 and the right-hand side is equal to 8 when n is equal to 1. So that means our base case holds. That means that statement is true when n is equal to 1. Now let us move on to step 2. Step 2 is our assumption, which is when n is equal to k. So we're going to assume, and we're going to replace all the n's with k's. The sum of r equals 1 up to k of r 2r plus 6 is equal to 2/3 k, k plus 1, k plus 5. Now notice that we replace the n's with k, not the r's. In this sigma notation, remember the r is a dummy variable to represent what we're substituting into the sigma notation at each stage. The n was how many bits we're adding together. It is the n that got replaced with k, not the value of r. Now we move on to step 3, which is our inductive step, where n is k plus 1. It's always useful to start with what we want to show, which is exactly the same thing as above, but instead of k, it's k plus 1. So replace the k with k plus 1, and then 2/3 k is going to be k plus 1, k plus 1 is going to become k plus 2, and k plus 5 is going to become k plus 6. So this is what we are trying to show in this particular example. So we start with the left-hand side of that, and we're going to use the first trick that we saw in the previous video. And that trick was, if we're taking the sum from 1 up to k plus 1, that's the same as doing the sum from 1 to k of that thing plus the k plus 1th term. So remember, this is a sum. It's do it when r is equal to 1, plus when r is equal to 2, plus when r is equal to 3, plus, all the way up to when r is equal to k plus 1. This is that whole sequence when r is equal to 1, plus r is equal to 2, plus r is equal to 3, up to r equals k. So this is the first k terms of the k plus 1 terms in this series. But we need to add on the k plus 1th term, and the k plus 1th term is when we substitute k plus 1 into this thing. So r becomes k plus 1, which is k plus 1, times 2 lots of k plus 1 plus 6. So this thing here is substituting r to make it k plus 1. And that's the first step. With these sigma ones, it's always going to be like that to start with. Split it up. Next step. Well, now we can see that that bit in green is equal to our assumption. So we can replace that whole thing with the other side. So we're going to replace that with 2/3 k plus 1, k plus 5. And we're going to keep this as it is for now. And I'm going to simplify this little bit here, which is going to give me 2k plus 2 plus 6, so that's 2k plus 8. Now I've managed to get rid of the sigma notation, I can try and simplify this algebraic expression. Now the way I'm going to do this, well, what I could do is expand this whole thing. So there's two ways to approach this. I can either expand this whole thing, expand the right hand side here and show they're the same. That is a perfectly valid way of doing this, and some people prefer that. I would say it's a little bit longer than the way I'm about to show you now, but possibly a little bit easier. But let's look at the way that I think is more mathematically nice. And the way we're going to do that is we're going to think, well, we know that we want to have 2/3 k plus 1 in our final answer. And we notice that we have a k plus 1 in both of these parts. So we're going to factorize out that k plus 1. But I'm not just going to factorize out the k plus 1, I'm actually going to factorize out 2/3 k plus 1. And the reason for that is because I know that I want 2/3 k plus 1 at the end. That's why the want to show is quite helpful, because I know where I'm aiming. Okay, so now let's think about what am I multiplying by the 2/3 k plus 1 by to get each of these things. For the green bit, I've got the 2/3 and I've got the k plus 1, so I need to multiply it by k plus 5. Right, if you imagine expanding these brackets, you would get that green bit above. Now, I've got the k plus 1, I need to multiply by 2k plus 8, but I've also got an extra 2/3 that I don't want. So how do I cancel that out? Well, 2/3 multiplied by 3/2 would cancel that out. Now again, if you imagine expanding this out, the 2/3 k plus 1 times by this, we would get this red term here. So now I have 2/3 k plus 1, which is the first bit I wanted. And then in here I've got k squared plus 5k plus 3/2 times 2 is 3k, and 3/2 times 8 is plus 12. So that's 2/3 k plus 1 times k squared plus 8k plus 12, which is a quadratic that I can factorize, which is 2/3 k plus 1 times, well, two brackets here, both beginning with k. They multiply to make 12 and add to make 8, so that's plus 2 and plus 6. And that, if we look back at what we wanted to show, is exactly what we wanted to show. So that is equal to the right-hand side. This is a proof by induction, so we always finish it the same way. We always finish a proof by induction with step 4, which is our conclusion. And our conclusion says pretty much exactly the same thing as it always does, with the one change from the previous one, which is that it has to be n equals 1, because our base case was n equals 1. Let's have a quick look at that inductive step again, because it is a little bit challenging. In particular, let's think about what's happening in sort of this manipulation here. If you did not like doing this factorization step here, that's perfectly okay. What you could do, as I said before, is expand these things. You could expand this one out, and you could expand this one out, and show that those two things are the same in their expanded forms. That's also a perfectly valid way to do this. And if you didn't understand that factorizing process, then you might want to do that. As I said before, that is a slightly longer process because expanding this is going to take quite a few steps and expanding this is going to take quite a few steps, but it's probably a little bit simpler to understand what is happening. So feel free to do it that way if you prefer. You should get the same simplified polynomials at the end of both of those steps.